This is based on joint work with Ben Hayes, David Jekyll, and Thomas Sinclair. So the history of all this goes back to a result of Popa, where he proved that L of z sitting inside L of n in this free product way is a maximal amenable algebra. And this was a significant result at the time for a number of reasons. First of all, it answered this question of Caddison from 1967 at the famous Baton Rouge conference, where he asked, is it true that every self-adjoint element of a 2-1 factor is necessarily contained in a hyperfinite subfactor? So due to Kahn's 76 work, we can see that Popa's theorem proves that the answer to this is in fact no. It was also significant, this result of Popa, because it was the first example of a maximal amenable algebra that came out of an abelian subalgebra of a 2-1 factor. And the way he proved this was by studying L of z central sequences inside of L of n, using his asymptotic orthogonality property, which is a powerful technique that is still used to this day and sits inside this collection of methods called deformation rigidity theory. So what we did is basically found a different way, a different approach to prove this that used more free probabilistic and random matrix theory methods to prove more or less the same results. And there's some overlap between his result and our result, and but they don't entirely eclipse one another. So the main technical idea that you need to understand in order to sort of see our theorem is this notion of one-bounded entropy. So this was first defined implicitly by Kenley Jung in 2007, but then much more explicitly worked with and expanded on by Ben Hayes in 2018. And it's an invariant for an inclusion of von Neumann algebras. You start with a tracial diffuse algebra M here, and then N is going to be a subalgebra. So throughout this, less than or equal sign is going to be my shorthand for saying that it's a sub von Neumann algebra. Then the one-bounded entropy of N in the presence of M is this quantity H, N colon M. It can either be minus infinity or anything between the values of 0 and positive infinity. And very roughly speaking, what it measures is if you take generating tuples, X for M and Y for N, then it measures asymptotically how many tuples of matrices you can find that whose joint distribution with respect to the normalized trace is approximately the joint distribution of the trace of this generating tuple with respect to the trace on M. Okay, and so there's some ways to make this more precise. I'm not going to go into details there, but if you're familiar with it, you can see that this is somehow a technical modification of Voiculescu's microstates free entropy dimension. So some other notation when we're just talking about the inclusion of M inside of itself, we'll denote that by H of M. And then we say M is strongly one-bounded whenever this quantity is finite. As I said, I'm not going to give you the explicit definition for this, but rather I'll try and flesh out the picture of it with some examples. So first of all, this will be negative infinity exactly when M has some subalgebra that fails to, with separable predual, that fails to embed into R omega. So if in particular you assume that M itself embeds into R omega, then this quantity is sort of behaving more nicely. And the minus infinity case is saying that like the situation is bad. So for the rest of the talk, we'll be assuming that we're in the case where we embed into R omega. And so we really only are thinking of this, this invariant as being valued between 0 and infinity here. And then in that case, this quantity will always be 0 if the subalgebra N is diffuse and amenable. This will obviously be relevant for how we recover Popa's result. Some other situations for when you know this quantity is 0. So talking about the one-bounded entropy of just a single von Neumann algebra, it's 0 if it has a Cartan subalgebra, or if it's non-prime, or if all of its non-zero direct summands have property gamma. Okay, so the one-bounded entropy can detect properties like this. And I mean, I already said this above, but it's worth mentioning again, this is an invariant of the von Neumann algebra. And while you know what it is for the free group factors, unfortunately, though, it's always minus infinity or always positive infinity. So it's not going to allow us to distinguish the free group factors. But due to recent work of Brandon and Verneau from 2018, you can use it to distinguish some von Neumann algebras. Namely, what they showed is that these free orthogonal quantum groups, the von Neumann algebras associated to these, have finite one-bounded entropy, so they're strongly one-bounded. And consequently, you know then, therefore, that they can't be isomorphic to any free group factor. Okay, so you can distinguish some von Neumann algebras, but not the one that everybody wants. I guess I should also mention that the only cases where this quantity has been computed, it's shown to be either 0 or infinity, so it could very well be that those are the only values it actually takes, but there's a priori no reason to suspect that it couldn't take something strictly between these two values here. Okay, so the theorem that we proved is the following. Let's say P and Q are von Neumann algebras that each embed into R omega, and take M to be their free product. So then whenever you have a von Neumann algebra N, you can guarantee that it sits inside of the subalgebra P, provided it has 0 one-bounded entropy in the presence of M and intersects P diffusely. So it's really easy to see how this recovers Popa's result. Here's the proof. Just take P to be L of Z, Q to be L of N. These both obviously embed into R omega, and then this makes their free product L of N. And then now say we've got some subalgebra A that contains P and is amenable. Well, then obviously its intersection with P is just going to be P again, which is diffuse. And moreover, since it's amenable, we know that it has one bounded entropy equal to 0 by example 2 on the previous slide. So just by then invoking theorem A, we get that A has to actually be contained in P, and therefore we get equality, meaning P is maximal amenable. So I should also mention that this isn't the most general version of this theorem that we proved, but I kind of wanted just to keep it simple for things. We can extend this in a couple of different directions. So one is that you can replace this scalar free product with an amalgamated free product over a totally atomic subalgebra D. And another way to extend this is that, well, due to work of Ben, you know that you can maintain this condition of having zero one-bounded entropy if you replace N with the von Neumann algebra, say, generated by its normalizer or its quasi-normalizer or a variety of other objects. So in that case, you can replace N with one of these normalizers, or the von Neumann algebra generated by it, and then just require that the intersection of P with that normalizer is diffuse. Okay, but for the purposes of this talk, we'll stick to this sort of simpler version of the theorem. And well, the way you prove this theorem is by proving a more technical theorem, as these things tend to go, and that's the following here, which I'll call Theorem B. So here we again have a traceable von Neumann algebra, and we have a subalgebra P. And we're assuming that we've got some tuple of generators, Selfadjoint, and then we also have a sequence of tuples of random n by n Selfadjoint matrices that satisfy the following list of conditions. So the first condition is that these play the role of microstates for your generating tuple. That is, they're uniformly norm-bounded for each I. And then if you look at the moments of these random matrices, sorry, I should be inserting a conditional expectation here. Oh, no, never mind. The moments converge in probability to the moments of your generating tuple X. So this is just saying that these random matrices are approximating the distribution of these generators X. And the second condition, exponential concentration, I'm not even going to bother reading it. This is just what's somewhat a standard assumption in random matrices, or maybe not standard, but is relatively common. So for example, most nice random matrix ensembles satisfy this kind of exponential concentration condition. The GUE, any sequence of random Haar unitaries, any random matrix ensemble that satisfies a common Schwinger-Dyson equation, they all satisfy this exponential concentration condition, okay? And this microstates condition also is of course, a very standard thing in random matrix theory. So these first two conditions are sort of unsurprising if you're doing anything in random matrix theory. But this third condition is something new, and we're calling this the external averaging property. And this is the only place that this subalgebra P really appears in the hypotheses. So you assume that for any polynomial P, the two norm of these expectations of polynomials converge to the two norm of the expectation of that same polynomial in X, but you take the expectation, the trace preserving expectation, onto this subalgebra P. So typically you would actually assume that this would hold if without this EP, that it would just converge to the 2 norm of P of X. That's be more or less saying something similar up here. But we're asserting this different condition here, that somehow this collection of random matrix ensembles, that they detect the subalgebra P in this way. So under all of these assumptions, you get the same exact conclusion that you had in Theorem A. Anytime you have a subalgebra, you can assert that it lives inside of this subalgebra P, provided it has 0, 1 bounded entropy in the presence of M and diffuse intersection with P. So I'm not, in the interest of time, going to mention the proof of how you go from, I won't go into detail about how you prove Theorem A from Theorem B, but for the experts, it might be sort of obvious. I mean, you just show that that in this free product situation, you have this microstates, exponential concentration, and external averaging properties. And well, let me flash back to Theorem A real quick. The fact that P and Q embed into R omega tells you that you've got lots of microstates lying around individually for P and Q. And well, since they sit inside free position inside of M, you can turn the microstates for P and Q into microstates for M by conjugating one of them by a random Haar unitary. This is due to work of Voiculescu that says that asymptotically then they'll be free. And so you get this microstates condition more or less for free. And then exponential concentration you also get easily, just because the only randomness in these microstates will then be precisely coming from the Haar unitary, which is known to satisfy exponential concentration. And then the external averaging property, you check more or less by doing some tricks with free products and computing some moments there. So it's relatively straightforward, especially in this free product case. Although in the case when you're maybe assuming that you're taking an amalgamated free product, the proof becomes quite a bit hairier and is not so obvious there. But what I'd like to spend the rest of the time talking about instead is showing how you would prove Theorem B. And the main technical tool that we use for this is a notion of a certain L2 functional calculus that was explored by David Jekyll in a couple of his earlier papers. So to get into that, let me establish some terminology here. So by a tracial non-commutative law, I'll mean a linear functional like this. So first of all, we're going to have a fixed tuple of positive numbers Ri, and then sigma r is going to be all linear functionals from, this is the algebra of abstract polynomials into C, satisfying these 4 conditions. So I want them to be unidal, I want them to be positive, and I want them to be tracial. And then the last condition is this exponentially bounded condition. I want the value of a monomial to be bounded always by the product of these R's, okay? So then we can take this family of linear functionals and we can endow it with a simple topology of just pointwise convergence on this algebra. So an easy example of this is, well, take any tuple of self-adjoint operators in M, then choose the R's to each be bigger than the operator norm of the xi's. Then their joint law, lambda x, which is defined, the linear functional defined in this way down here, will be an element of this sigma r. Okay, and so this exponentially bounded condition comes from precisely the fact that you have these operator norm bounds. That's all that's really being encoded in there. And moreover, you can check by a variation of the GNS construction and show that actually every element of sigma r really arises in this way. It really does look like the law for some actual honest-to-God operators in a von Neumann algebra equipped with a trace. Okay, so now using these non-commutative laws, we're going to construct a C-star algebra. And again, this appears in somewhat different forms, but in spirit is still very much the same in work of David's from 2018, 2019. So again, for a fixed tuple R, I'll let this script AR be the following algebraic tensor product. So continuous functions on our space of tracial non-commutative laws, tensored against this abstract polynomials. And now for each X in some von Neumann algebra satisfying this norm boundedness condition, we could define a map, an evaluation map going from AR into M in the following way. So for the first tensor factor, you just evaluate it under the non-commutative law of this tuple X. And for the second one, you just you plug in the operators into the polynomial, and this gives you some element in the von Neumann algebra. So I'm immediately going to abandon this evaluation notation, and instead for a general element, I'll just write f of x for this, the image under this evaluation map. Okay, so now using this, we can define a semi-norm on this space, which I'll call the R2 norm. And you look at the supremum over all tracial von Neumann algebras and all tuples x satisfying this operator bounded condition, operator norm bound condition. And then you just look at the 2 norm of the image of f under the evaluation and take the supremum over all these things. So this gives you a nice semi-norm, and then you do the typical thing of modding out by the kernel of the semi-norm and then take it to completion. And we'll call script FR2 the completion of this map. And of course, these evaluation maps still lift nicely to this space. So you can still evaluate these things and get objects in the von Neumann algebra. And then we'll push us even further. We're going to define another norm, the R infinity norm, to be the sup over, again, the same collection of von Neumann algebras and operators X satisfying this norm boundedness condition. But now you're going to look at the operator norm of their images. Okay, and this may be infinite, but then we'll call the subset of elements for which you get a finite value under this norm FR infinity. Okay, all right, so the punchline for all of this is that this FR infinity is going to be a C-star algebra under this norm, and it's going to satisfy some nice properties with respect to these non-commutative laws. So you don't really need to remember any of this aside from the fact that you've got this algebra FR infinity, and you can evaluate these to give you elements inside a particular von Neumann algebra. So the proposition is the following. So as I said, this gives you a C-star algebra with respect to this norm. And additionally, if you fix a tracial von Neumann algebra and take a tuple satisfying this bound condition, then in fact this evaluation map is a surjection onto the von Neumann algebra generated by X. So meaning you can take anything in the von Neumann algebra of X and witness it as f of X. You can witness it as some evaluation of some, we'll call it a function for an element in R infinity. And then moreover, say you've got some convergence of laws here. So remember that just means pointwise convergence on the abstract polynomials. If you have convergence of a sequence in this way, then that passes through convergence when you evaluate these two new operators under any element in this R infinity thing. Okay, and then lastly, these are uniformly L2 Lipschitz in the following sense. So given some fixed FR for any epsilon, there exists a delta, so that if you have a pair of tuples satisfying this operator norm bound condition, then being close in L2, being delta close in L2 for every entry in the tuple guarantees that you'll be close in L2 under the images under this map F. Okay, so this is a relatively powerful L2 functional calculus. And the main things that we'll need for this to prove theorem B is property 2 here, namely that we can witness any element in the von Neumann algebra generated by X as the image under this evaluation map, and property 3 here, that convergence of these laws passes to convergence after you do evaluation. All right, so let me remind you about theorem B here. So again, the context is we've got this tracial von Neumann algebra, P is a subalgebra, X is a generating tuple for M, and A are these nice matrix, random matrices that are approximating the law of the X's. They're acting as microstates. Okay, and then N is going to be a subalgebra, which will assume to have one bounded entropy equal to 0 in the presence of M, and diffuse intersection with P. All right, so how do you end up proving this? First of all, just fix an element y in N, and then because this evaluation map is surjective, we can find some f in FR infinity that witnesses y in this way. And if we're going to show that y lives in P, we just have to show it equals its own conditional expectation onto P. So that will be the strategy. So first of all, the microstates condition is really saying that if you look at the joint law of the ANs, then this converges to the law of the X's. And so again, by property 2 of that proposition, that means then that if we look at the joint law of their evaluation under F, And remember, it still makes sense to evaluate these things because this was like a sort of universal L2 functional calculus. Then these will likewise converge to the joint law of Y. Okay, so what that means is that the random matrix ensemble that you get out of this evaluation are acting as microstates for Y. They're obeying the same norm boundedness condition, and their moments are converging to the moments of Y asymptotically. All right, and then, well, okay, you kind of pile all the other hypotheses together, the exponential concentration, external averaging property, one bounded entropy being 0, and diffuse intersection. You put all these together, and what these produce for you is what's called microstates collapsed for Y. And what that means is that anytime you have two microstates for Y, they have to be close together. In particular, they are all close to a single deterministic family of microstates for Y. So what that means is that you can find some deterministic matrices Bn, a sequence of them, so that any microstates for Y, in particular these FANs, have to asymptotically get close to the Bns. Okay, so all of the microstates sort of collapse down onto this single family of microstates Bn for Y. All right, well, now if you think about it, what we're doing is we're measuring here how close this random matrix is to a deterministic matrix. And so therefore you can bound this below by replacing Bn with its expectation, the expectation of this random matrix ensemble, okay? Which of course gives you the sort of the closest distance between this random matrix and deterministic ones. Now, using this external averaging property again, remember that was telling us about the behavior of these conditional expectations. It turns out that's equivalent to saying that actually this limit converges precisely to the following two norm, fx minus this expectation of xx. But of course, that's exactly y minus its expectation. So in the end, we've shown that y is equal to its own conditional expectation on the p, and therefore must naturally lie in n. Okay, so that completes the proof and also my talk. Thank you for your attention.